Alrighty, welcome back to part two of lecture one of big data for statistical learning. Um, Here we have various categories of machine learning: supervised, unsupervised, semi-supervised, and then reinforcement learning. Supervised learning. Actually, let me see if we get into these on the. Of course, we do. Supervised is where a human or programmer or whoever provides a set of labeled data. Again, labeled being that terminology that we used, that providing of the ground truth, that providing of an expected value, um, whether that comes in the form of a bounding box or a target sentence or um, some form of expected forecast. um Labels the truth, the expected values that we assign to data. Supervised learning makes use of that. A fully labeled data set, fully labeled samples. Um, and we give it inputs and outputs with the answers and let it learn the relationship between them, the inputs and the answers. And then, of course, it adjusts weights on the various neurons in order to format that, you know, until it gets the outputs. Most machine learning is done in a supervised fashion with these labels. Unsupervised learning is used without labels. This is kind of similar to the data mining example with k-means clustering that I used in the prior video of this lecture series. Boop, boop, boop. Let me see. I'm going type in some, so k-means clustering. Go and pull up a quick video, not a video, sorry. This is a great example. Oh, take your time. Oh, this is the it's a simple photo, but I like it for these. No, I lied. I want to use this fancy photo. Um, Share screen. It means clustering. Okay. So now you should be able to see my Google. Um, and here we have k-means clustering. Here we have a large set of data, large set of data, large set of data. And it's formed of one entire set, but is separated out into three various clusters. And there is imagine the middle point of this data, right? Let's say the middle is like here. It K-means clustering works by measuring the Euclidean distance from the proposed centroid or center of these clusters, right? And if, let's pick a random point, this far one on the right, it measures the distance from all centroids, all centers of these various groups, and determines the closest center and assigns it to that group. That's k-means clustering. Easy enough. This is a common unsupervised learning algorithm in machine learning. Okay. Anyway, back to slides. All right, so you should be able to see my slides now at this point. It's used on label without data's without labels, without ground truths, without expected values. Whether there may be too much data or um that just hasn't been labeled yet. Most of the data out in the world is raw data. It's not labeled. Labeling is a very expensive task in terms of time and man hours. Um, and the goal, how back to unsupervised learning, the goal is to find patterns or intrinsic structures in the data mining. Okay. Unsupervised learning is data mining. A good way to simplify data, however, reduce the dimensions and remove unnecessary variables, or it can be used to detect anomalies or outliers in the data. Clustering is one of the most common unsupervised learning techniques. And yeah. And then you have semi-supervised learning, where we use partially labeled training data sets, a small amount of labeled data with a large amount of unlabeled data during the training phase. Semi-supervised learning falls, of course, between supervised and unsupervised without any labeled training data. Let's see. The trained models that result from this training set can be highly accurate and less expensive to train when compared to using entirely supervised learning strategies. So here we have labeled data, labeled and unlabeled. Oh, and then you have a delineation between supervised learning, the classification pane, and then this classification pane. And you see how along this line, this division that it groups here, um, other unlabeled data, we don't know if these are triangles or not, but based off of their proximity and similarity to the labeled data, we infer and forecast these as triangles. Reinforcement learning, this is most commonly seen in like automated driving. There's this famous, we'll get into it way later. I'll do a lecture series on, it'll be titled like modern AI, but it is actually a class, an entire class on reinforcement learning, and the Monte Carlo problems and the simple grid worlds and it's another great application. I just recently got into chess. Chess was taught via reinforcement learning. That's how a lot of these big chess bots learn. AlphaGo, AlphaZero, Stockfish, Leela. Those are some of those are chess bots. I don't know if they all use reinforced learning. I'm sure maybe. But anyway, principle remains the same. Reinforcement is the the model is learned from a series of actions by maximizing a reward function. And then you penalize bad actions and reward good actions. Ultimately, the the bot, the bot, the model seeks to optimize its function so that way it can reap the largest reward and incur the lowest amount of penalties. A popular example of reinforced learning would be a self-driving car, getting feedback from the environment. Typical framing of reinforcement learning. An agent takes actions in an environment which is interpreted into a reward and a representation of the state, which is then fed back into the agent. Okay. So yeah, a self-driving car, a great example. It recognizes similar states, right? So it knows that if I'm going 60, but I'm only 3 feet away from something, that I have a high probability of hitting it. This is not how the decision gets made by the car. But that being said, um, oh my God, I'm gonna break my fucking screen. Forgive me. There's a fucking fly that keeps coming back and it's pissing me off. Um, it doesn't know the necessarily the problem. It knows that in a similar state, it's received a negative outcome, so it'll attempt to leave that state into a better one. Is more the point that I wanted to make. Um, yeah, so you have an interpreter that assigns a reward, um, and the bot will take an action. It gets some feedback from the environment, and then the interpreter will report on the reward and the state back to the model. Choose a suitable algorithm. Unsuitable algorithms will result in low accuracy. So here, you got to know the state of your data. Whether you're doing linear trends or polynomials or things of that nature, you can model data however you want. Just know your accuracy is greatly affected. Okay. Data in a nonlinear. I can't fucking kill this thing. I can't hit my screen that hard. All right, I got something for his ass. So using a linear regression method would create much larger errors than necessary, just because you're using the wrong model. It'll still regress, be able to perform regression and model it, but it won't do so accurately. Here are some machine learning algorithm examples. So you have supervised and unsupervised learning. Of course, you have clustering, k-means, and then you have k-means clustering, which is super cool. I'm actually not familiar with some of these. Logistical regression, of course. Fuck, what is SVM? The stochastic. Oh fuck, I can't remember that one. Neural networks, decision trees, random forest, um, naive Bayes. What does that say down there? The Gaussian. Oh, I don't know. Can't read it. Which algorithm should I use? Selecting a machine algorithm is a process of trial and error, but choosing the right algorithm can seem overwhelming. There's tons of options. Finding that right algorithm is partially just trial and error. Even highly experienced data scientists can't tell you whether an algorithm will work without trying it out. Um, so some of the questions that you should ask is the size and quality of data. Um, whoa, and the nature of your data. Whoa, what's happening? The availability of computational time, the urgency of the task, and what you want to do with it. So, the breakthrough of machine learning. Let's see, deep learning based on. Oh, sorry. Okay, yeah. So, deep learning is machine learning algorithms based on multiple levels of representation slash abstraction. All right. So, in one of the models that I'm familiar with, the YOLO model, in the version 7, there's actually what we like to call a feature pyramid, where low-level features are extracted. So, low-level features may be the shape of an object, and then it's a feature pyramid, and each layer that stacks on top of one another are finer grained and higher level details or features of the data. So here we have, this is a fun graphic for the distinction of deep learning versus machine learning versus rule-based systems. This is your typical code. All right. This is typical code. I have some input. I have hard-coded rules, hand-designed program, and I get an expected output. The computer follows my rules to a T. Okay. Then we have classical machine learning. All right. We have some input and some, and again, probably still some design features, but then we create a mapping from these features to give us an output. We have representational learning, which is follows a similar structure as classic machine learning. Then we have deep learning, which is the feature extraction. Okay, feature extraction is key, and it does so in layers, right? So again, simple features, most complex features, and then mapping of these features, mapping of that input to various weights and branches to the output. Here we have a little thing about AlphaGo. Again, the Go is a game. Don't know shit about it. You place checkers, dots at little intersections in an attempt to, I think, block off the most space, um, and control the most territory, I think is what Go is. But anyway, similar to chess, there's AlphaGo and AlphaZero, both bots that have surpassed human intellect uh, by a massive margin, by just learning and playing thousands of iterations of games. Um, Let me see what else. Um, who was I think it was Bob, no, was it Kasparov or Fisher? I think it was Kasparov that played Deep Blue. Um, let me check that real quick because that was the original. Was it Deep Blue? Yeah, let me see. Because I think it was, yeah, okay, it was Deep Blue, the original chess computer that built by IBM. Um, and Gary Kasparov, the world's greatest chess player at the time, actually played against this bot um, in a series of 3 games. Lost the first game. He lost the first game. He went and found, I mean, ancient chess technique from like the 1200s or some shit. And of course, because the Deep Blue was trained on modern day chess theory, it lost in a game that it had never seen before. It was a novelty. That night, they went and trained it on all the old shit. And from that point forward, computers have not lost a man. It was fucking crazy. Here's an illustration of deep learning. Function of mapping from pixels to an object is grossly complicated. So we have a series of hidden layers to extract increasingly abstract features. Okay. So if we look at the individual pixels here, we may have a shape. I mean colors. We have a color. And these are individual pixel values. And then the first hidden layer probably performs some form of convolution, right? To detect edges. Second hidden layer to detect contours. Third hidden layer is maybe various parts of an object. And then based off of the values of the input, maps it through this network and determines, what category it falls into. Here's a little bit about the history of deep learning. I won't go into that too much. Increasing accuracy. Okay, so that's the error rate. So as we can see in 2015, the error rate dropped below 5%. So here we have the branch of deep learning, right? So we have convolutional neural networks on image processing, recurrent neural networks for machine translation, so like Google Translate, generative adversarial networks or GAN networks, and then you have autoencoders. The type of deep learning is a type of machine learning that improves with experience and data. Its only viable approach to build true AI systems in the real world and obtains its power via a nested hierarchy of concepts and feature extraction. So yeah, and then the more abstract the representations computed in terms of what? More abstract representation. I can't read that shit. Big data. Okay, that's cool. Oh, went too far. Big data characteristics. A lot of volume, quantity of generated and stored data, has a large variety in type, may have a different velocity. Let me see what velocity means. Speed at which the data is generated and processed. Ah, yes, big data will typically flood in. I think the average person generates like gigabytes or terabytes of some shit of data over the course of like a week or a month. So like the amount of data that we make that is out there is absolutely insane. And then here we have the veracity or the data quality and value. Big data comes from everywhere. Comes from your communications, your vehicles, machines, medicals, sales, transactions, everywhere. Big data means the Internet of Things. With everything having being connected to the Wi-Fi, with everything transmitting signals and sharing information, data is only going to grow in popularity. The volume is going to increase, the quality is going to increase as we get it from so many different sources. Let's see, so these are just these are tools that we can use in order to process and perform, actions with big data to analyze it to and make machine learning models. We can apply these everywhere. With transportation, we can do insurance adjustments based in areas of natural disaster. The XView2 data set uses satellite imagery and natural disasters for insurance claims. banking and security, fraud prevention, your spam filter in your email. Sometimes those use AI. Healthcare and diagnostic areas. It was images were used to diagnose patients with COVID-19 from chest x-rays. You could use in a smart grid in energy with seemingly automatic load balancing. Um, Maybe in education, Duolingo uses some form of AI and machine learning to customly cater your mistakes and lessons and areas you need to improve, custom education plans based off strengths and weaknesses. Of course, you have GAN networks here with media and entertainment, the uh, generating of movies, snippets, songs, art, all here. And then manufacturing finally. How would AI play into manufacturing? Ooh, okay. Um, Amazon with the driving bots that take, it's a bunch of people's packages and they just drive around this little warehouse. There you go. Available data, huge data, and then your ability to do some shit with the data. To harness this much data, it's just it's not feasible. The man time it takes to label everything is insane. So we got to work with what we got. Maybe make an AI that is highly reliable and can label data for us, or generate synthetic data with GAN or generative adversarial networks. Um, that only adds to the problem. Massive amounts of data, though. Challenges of big data, the uncertainty of data, synchronization across data sources, and then the scalability of a big data platform. Big data analytics, I'm not going to go into that. And then finally, we have our summary. Um, Machine learning involves many topics. Constructing machine learning methods depends on specific problems. Deep learning cannot handle all the problems, and big data analysis needs machine learning. Thank you very much for your time. I just want to scroll back to the top, give credence to Dr. Shishwan Dong, his amazing amount of work, not only as my professor, but his contributions, projects, and things in the machine learning landscape. Thank you.